Hello and welcome to step 5, implementing the convolutional neural network variational autoencoder, the CNN VAE. And mostly, welcome to the first implementation phase, because indeed, you've just seen in the 4 previous steps the required theory you needed to understand before implementing, of course, the model. And so, what we're about to implement in this step 5 is exactly this part composed of the CNN and the VAE. And what's important to understand is that the CNN, the convolutional neural network, allows the vision of the model so that the model is able to see, just like a human, the input frames on the game, on the car racing game, just as if it was playing the game like some humans would play video games. And then the VAE, this part here, is the part that dreams. Remember that the specific feature of this new full world model is that it is a model that is able to dream, because indeed the core added value of the full world model is that it gains better performance inside the dream, that is, inside the reconstructed environment happening here in the VAE. So basically, we call it a dream because, when we dream, when we humans dream, well, what happens is that our brain remembers the real environment of Earth in which we live, and during our sleep, our mind reconstructs the environment images that our brain remembers. And sometimes it's true that the dreams seem quite different from the reality because the reconstruction can be very abstract. That's why sometimes we have very weird dreams. And so here that's the same. We have the input frames, which are the reality, the model sees it, and then with the VAE happening here, well, the model will first encode the real images, the real input frames into what we call a latent vector, which you saw with Kirill in his variational autoencoder intuition lectures. And then from the latent vector, the VAE will reconstruct the images as in a dream. And that's why here, this whole VAE part of the full world model corresponds to the dream. And then, of course, we have the memory. We will see that and implement that later on, but that will, of course, improve the model because it will leverage the temporal relationship of the environment to be able to predict some better future actions. But that will come in step 6 with the recurrent neural network, then step 7, mixture density network, and then again, we'll implement together the MDN-RNN. Alright, so here we go for this step 5, implementing the CNN VAE. I can't wait to start. We're going to build a big class that is going to contain not only the full architecture of the convolutional variational autoencoder, but also we will implement the training operations. So this will take about 80 lines of code. I hope you're ready. And now the exciting thing that I wanted to show you is that the architecture that I've just mentioned and that we're going to build in this implementation, in this huge convolutional VAE class, is going to be exactly the same architecture as the one given in this article. Because indeed, here, that's the part explaining the VAE model. Make sure to read it. If it's not done yet, you'll get the right intuition. But if we scroll down to the putting everything together section, you'll see at the end that for more specific information about the models, training procedures, and environments, please refer to the appendix. And if you click it, well, you will find out the whole architecture of the variational autoencoder. And so what I was saying is that the architecture we will build in our implementation of this step 5 is exactly that same architecture that we see here. Meaning some first convolutional layers of 32, 64, 128, and 256 tensor inputs. Then we'll create a latent vector, which will be a one-dimensional vector, of course, but composed of 1024 elements, which will be the result of the flattening after the convolutions. And then we'll use the deconvolution, or also called the transposed convolutions, or even the inverted convolutions, to recreate or to reconstruct the images from the latent vector Z. All right, and this will create the dream right here. The dream is created right here. That's the reality, the input images coming from the environment, and all this process happens to create, in the end, the dream. And so this is really fascinating because the AI manages to gain performance, to become stronger and more intelligent by training inside the dream. So that's why, remember, I said one of the pros was that this whole invention is based on a fascinating idea. All right, so if you're ready, now we're going to move on to Python to build all this, plus the training operations. And so, speaking of Python, here it is. Right now, we are indeed on Python, but more specifically, we are on the Spyder IDE from Anaconda. So, if you like this IDE, you can download Anaconda, which you can find very easily on Google. And then inside Anaconda, you will launch Spyder. And eventually, at the end of the course, you'll see that we will create a virtual environment in which we will install all the required packages. And inside this virtual environment, we will, of course, execute the whole code. That is, we will run the full world model on the car racing environment, and we will play against it like I did in the first lecture of this course. But we're still far from that. Before we have to build our first model, the first model component of the full world model, and this is the variational autoencoder. And so, where is that vae.py file that I created? Well, first of all, no worries, because we will give you everything at the end of the course. You will get not only the inference folder, but also the training folder in both AI programming languages, which are TensorFlow and Keras. Here we will implement that in TensorFlow. But where did I create this VAE Python file? Well, here, as you can see, I am on my desktop. On my desktop, I created this AI masterclass folder. And if we open it, we will get, as you will get when we give you the folder, two subfolders, inference and training. And in the inference folder, that's where I created the VAE Python file, which we will implement in the step 5. Are you ready? Here we go. Let's start with the first code section, importing the libraries. So we will only need 2 libraries here to build this convolutional VAE class. And these are, first, NumPy, for which we will give the shortcut NP, and of course, as we've just said, TensorFlow, for which we will give the shortcut TF. And perfect, that's it. That's only what we'll need to create our convolutional VAE model. And now we're ready to build the convolutional VAE model, and we'll build that, as you can see, within a class, which we'll call convVAE. But this is going to be a big code section, a big class with a lot of things to do, including building the whole architecture, which, as you saw, is not a simple architecture, and also the training operations. So let's take a break here, let's get some good energy, and let's start tackling it in the next tutorial. Until then, enjoy AI.